All righty. All right, hopefully everybody can see the screen. And we're going to start with gases. This is the last hard chapter. All right, so we have gases. And the first thing about gases, we have something called kinetic molecular theory. No one ever says kinetic molecular theory. We say KMT. Kinetic molecular theory. And the idea of kinetic molecular theory, if we were to summarize it into just one phrase, it would be small, fast, and far apart. This describes gases, small, fast, and far apart. But if we were to say, in detail, we would say something that, gas particles are very small. They have to be small. So you won't find very large molecules being gases. All right, gas being the very air that you're breathing is a gas. All right, it's a mixture of gases. It's a homogeneous mixture. It's mostly nitrogen with a little bit of oxygen in there. Believe it or not, the very stuff that you need, called oxygen, is just a small part of what you're breathing. It's 22%, I believe. It's either 22 or 24%. Is oxygen. The rest of it, most of the rest of it is nitrogen, but it is a gas. And nitrogen molecules are small. Oxygen molecules are small. There are literally, there's a nitrogen molecule, and here is an oxygen molecule. And hopefully everybody knows what the geometry is of these two gas molecules, and they're both linear, right? They're both linear. They're two bonded, no lone pairs. Okay. So let's see who's here. Let's see, participants. Got a pretty good group today. All right. And so those are gas particles, and they're very small. So you won't find very large particles. All right. Now, gases are mostly empty space. In other words, the distance between the particles is large compared to the particles themselves. So the very air you're breathing is mostly empty. There's some molecules here and there floating around, but it's mostly what you feel is just a few molecules. There's not really a whole lot of stuff as far as the atmosphere goes that you're breathing. Not a whole lot of stuff there. And so it's mostly empty space. So it is large distances between the particles, and they behave as if they are points or point masses. What does that mean? Point masses, it means literally these little green dots I'm putting up here, this would represent a gas. They're just literally flying around like they don't see each other, like they're little points. They have no, and a point means that they have no volume, and so they're volumeless points. That's what it means to be a point mass. That's how they behave. And that's going to be important later, because this is an ideal gas I'm describing here as versus a real gas. Okay. And so they behave as if they're point masses, and not only that, but they're very fast. Very fast and move randomly. Okay, so these little green dots I put up here, I mean, they're going all sorts of directions, but they're going pretty quick too. How fast are they moving? And we will calculate how fast these are moving. And it's about, for the air in the room that you're in right now, it's roughly about 550 meters per second. Now, put this in perspective, a meter is a little bit longer than a yard. And so the air particles in the room are moving roughly about 6 football fields a second. You know how big a football field is, right? It's pretty long distance. It's moving about 6 of those a second. I mean, they are really moving pretty quick, gas particles in the room. Now, why don't you feel a 600 yards per second breeze? That would be pretty fast, right? Why don't you feel it? Well, because they're moving randomly. They're just as likely to be moving in this direction as they are to be moving in that direction. And so on average, they cancel each other out on average. So since they're moving randomly, you don't feel this 550 meters per second wind. Okay, that would be really fast. That's about the speed of sound. So you don't feel it. So they're moving randomly. Okay, so that's gases. Now, that's KMT, kinetic molecular theory. Now, when we have gases, we have different units for gases. I'm going to switch colors because I don't want to use green anymore. And the first thing we have is something called pressure. All right, gas pressure. Now, if you look in your text, there are all sorts of pressures that are presented in the text. The SI unit is something called the Pascal. Okay, that's a kilogram per meter squared. Okay, we won't use those. All right, the pressure units that we will use will be atmospheres, otherwise known as ATM, and millimeters mercury. And an atmosphere is equal to 760 millimeters mercury. And what you may see on the TV when you are watching the weather, they'll talk about inches of mercury, and it'll be around right around 29.95 inches of mercury. We won't deal with that because that's an English unit. Okay, and these two units here, in the atmosphere and millimeters mercury, are not SI, but they're what we're going to use. So we have 760 torr. So a millimeters mercury is equal to torr, which is 760 of those is equal to an atmosphere. Okay, so these give you a conversion, and so you would say 760 millimeters mercury over an atmosphere. And of course, anytime you got something over something, you can use it as a conversion factor. In other words, we can go back and forth between atmospheres and millimeters mercury and millimeters to atmospheres. Okay, back and forth. And the magic number is 760. Okay, that's the units of pressure. Now, what is pressure? Pressure is the force on the container walls. Now, what does that mean? Well, let's see. And we take a look at a wall. Here's a wall. And we have gas particles. And what's happening is these gas particles, they whack against the wall, and then they bounce off. And maybe this one goes like this, bounces off that way. Maybe this one hits there, bounces off that way, and maybe this one's going that way. Okay? And so every time it hits the wall and bounces off, it imparts a force. It's kind of like if we had one of those machines that throws tennis balls. Got a tennis ball going, and you're throwing it at something like that. Here's a tennis ball. And as you can imagine, if one hits an object, it'll bounce it just a little bit. And if you have a whole bunch of them, like one of those comedy movies where they're just throwing millions of tennis balls all at one time, if they hit something, they're going to push it back. Okay, well, that's the same thing happening with these gas particles, except instead of a few of them, there's bazillions. Bazillions and bazillions are whacking against the wall of the container, and you perceive that as, let's see, let me make sure I unlock the meeting so more people can come in. And you perceive that as the pressure. So when you pump air into the tire of your car and you want it to have so many pounds per square inch, because that's what PSI means, is pounds per square inch. Well, that's you're pumping more and more air in there, and so you're getting more and more gas particles. They're going to whack more and more on the container walls, in this case, your tire. All right. And so the conversion for pressure for our purposes will be either atmospheres, torr, or millimeters mercury. Okay, that's pressure. Now, volume. That's the space occupied. And what we're going to use is, generally speaking, we're going to use liters. Now, the SI unit for volume, the space occupied, is meters cubed. But a meter cubed is pretty big. If you think about it, it's a box. It's a box this big by this big by this big. It's an impractical number for what we're going to use. So, like a lot of metric stuff, we just use whatever is convenient, and a liter's pretty convenient. That's why we use liters. The other unit for volume that we'll use is something called the milliliter, which is 1/1000th of a liter. So 1,000 milliliters is a liter. All right, so those are the two units. And then also, by the way, a milliliter is exactly equal to a cubic centimeter, which is exactly equal to something called a cc. If any of y'all decide to go into some sort of medical field, either you're going to become a doctor or nurse or something, or a veterinarian, you will see the term cc's, as in, you got someone who's having a heart attack and you say, give me 4.5 cc's stat, right? So many cc's stat, and what they're saying is giving me 4.5 milliliters of whatever. And stat means quickly. That's what stat means. And by the way, if you do become a nurse or a doctor, make sure that every time you say something, you say stat right after what you say. So yes, the answer is yeast infection. Stat. And then they will, they will all obviously think you're the greatest nurse or doctor ever. So make sure you end everything in stat. Yes, indeed. All right. So that's volume. And so volume is generally going to be milliliters or centimeters cubed. Okay. And sometimes you will hear it referred to as cc's, which is short for, by the way, cubic centimeter. Not much less writing, but that's what people have done. They have abbreviated something that's already short and made it just slightly shorter by calling it a cc. So that's the volume. Now, the next thing that we have is, let's see, we got pressure, we got volume, and we have the amount. The amount, now usually when we think amount of something, we think of the mass, and the mass of something is usually grams or kilograms. But in gases, we don't ever talk about grams. What we do is we talk about moles. Oh, wow, look at that. That's back from chapter 3 and chapter 4, isn't it? What did I say about chapter 3 and 4? It will keep coming back, right? It will keep coming back. You will still have to use the stuff from chapter 3 and chapter 4. Okay, and we have something called the mole. And anytime you have grams, and you often will, what are you going to have to do? You are going to need the molar mass. It doesn't go away. And that, of course, is grams per mole. And so you will need moles for gas calculations. And so how do we use moles? Well, we don't have scales which read in moles. We have scales which read in grams and kilograms and pounds and ounces, right? And so you will have to turn your grams into moles. It's just a given. Just like when we did, we had so many grams of something, and then we would say, how many grams would you get? Right? Remember that from chapter 3, chapter 4? All right. And what was the first thing you had to do? Anywhere where you saw grams, you would have to get the molar mass. It's the same thing here. When we do gas law calculations, and we will, the first thing you're going to have to do is convert everything that's in grams into moles. That's the first thing you'll have to do. Just like chapter 3, chapter 4. What was the first thing you had to do? Anywhere where you saw grams, you needed the molar mass. It was the first thing you had to do. So it's the same thing here. When you see grams, you will need moles, and it's the amount. Okay? All right, and the final, you got pressure, volume, the amount, and the final thing that we have as far as units for gases goes is the temperature. And, the temperature, the definition of temperature is the amount of internal energy. I mean, that is one definition of temperature. And the unit that we're going to use is something called the Kelvin. All right, otherwise abbreviated as big K. This is Kelvin. Now, we will mostly be given, most problems will be given in degrees Celsius. Most problems. But the first thing you have to do is add 273.15 to it, and that will give you Kelvin. All right. Now, you must use Kelvin. Now, why in the world did I write this in red with triple explanation points and underlined it 3 times? Why in the world did I do that? Why did I do that? And I'll tell you why. Because, if I can get rid of that, because you do not want to be that person. That's why it's in red. Do not be the person who uses degrees Celsius in a calculation. Do not be that person. You will make me cry. You do not want to make me cry, okay? When I see degrees Celsius used in a calculation, I say, why, God, why? Why? Why are they using degrees Celsius, okay? Do not use degrees Celsius, okay? And there's a reason for that. And it goes like this, all right? If you were to try to predict what the volume of something is with temperature, you would say some constant, lowercase k, times the temperature. Now, since we're all sciencey sort of people here, we're supposed to be sciencey sort of people. And one of the sad things about this whole COVID thing is I don't get to see y'all in person. So I can say, yes, Crystal, you are obviously a sciencey sort of person. And I can look at, say, Justin and go, not so sciencey. but we're all supposed to be sciencey sort of people, right? And the one thing that we should be able to do is we should be able to look at volume equals some constant times temperature, and we can say that as the temperature goes up, what happens to the volume? As temperature goes up, if the constant stays a constant, then the volume should go up too, right? Hey, this makes sense, right? And as the volume goes down or the temperature goes down, the other one goes down. And this is what it means to be directly proportional. All right, as one goes up, the other goes up. As one goes down, the other goes down. Okay, so far so good, right? And the other thing that we should know, being sciencey sort of people, is if K is positive and the temperature is positive, then the volume should be positive, right? Hey, so far so good, right? Now, here comes the thing. Around here in North Carolina, eastern North Carolina, of all places, flyover country, as I refer to it, because everybody flies over North Carolina. I know what eastern North Carolina. Out here, even out here in eastern North Carolina, does it ever get below zero as far as the temperature goes? And you may say to yourself, hell no, I'm looking outside and it's going to be 90 bazillion degrees today, right? And it's going to be hot, right? But let's think into the future or into the past. Like, well, maybe not this past January, because this past January it was like 70 almost every day, right? I mean, it was wonderful. Well, wonderful in the sense of air conditioning. But in a normal time, sure enough, it does get below zero. It gets below zero in North Carolina. About 3 years ago, maybe it was 4 years ago, I remember stepping out on my back porch and it was -5 outside. It was cold. It was -5. Now, it was -5. And so we look at this -5, and what do we see right there? I see a minus sign. It was that cold. It was minus. So we get minus temperatures, even around here in North Carolina, eastern North Carolina, of all places. And so what does that do to this right here? We put that in there, and now we have a minus. Now, what's a minus times a plus? We get a minus, right? So that means if the temperature is below zero, what's the volume? It's minus. And you may say to yourself, hey, what's the big deal? So it's a minus volume. What's up with that? I don't care. Wait a minute now. Is there such a thing as a negative volume? I mean, I have never seen a negative volume. I've got something that has a volume, right? Got this cube over here, and it gets smaller and smaller as we get colder and colder, right? But at some point, is it negative? I mean, once you hit zero, you hit zero. You're done. You're done, right? There is no such thing as a negative volume. You can't have less than nothing. It's kind of like my bank account. Oh, wait a minute. I better answer this. I got a text from my boss. Schedules will be whatever. Jeez, my boss. So yeah, pro tip here. Whenever the boss texts you, yeah, you should probably take a peek, right? Just saying, just saying. And guess what happens when the boss texts you? It's never something important. It's never something important. And it's like, why in the hell did you text me? All right, fine. All right, pro tip, just saying, just saying. All right, so you end up with a negative volume. There is no such thing as negative volume. Okay, and that's one of the problems with using degrees Celsius is you can have negative temperatures. And that's one of the problems with using degrees Fahrenheit. You can have a negative temperature. If you can have a negative temperature, you can have a negative volume. We can't have negative volumes. All right, and so Kelvin has no negative temperatures. Kelvin has no negative temperature. All right. Once you hit 0 on the Kelvin scale, that's it. 0 on the Kelvin scale is called absolute zero, and it's called absolute zero because, well, you absolutely cannot get less than 0 on Kelvin. Remember the whole definition of Kelvin back on day 2, weeks and weeks ago, day 2, right? And I said, or maybe it was day 1, I don't remember, but I can tell you that the whole idea of temperature, one of the ideas of temperature is the molecules are bouncing back and forth, all right? They're wiggling. And as you cool them down, they get slower and slower. And eventually, if you cool things down enough, they stop. Can you be less than stopped? And the answer is, well, no, you can't be less than stopped. And so we put that point as being 0 Kelvin. So we end up with no negative temperatures. Okay, and this is important. Why is it important? Because if you use something other than Kelvin, you will make me very sad. You will make me very sad because you will end up with something crazy like a negative volume, and you will say, well, what's the big deal? It's a negative volume, it's a negative pressure. And I will say, I'll see you next fall. All right, I will see you next fall. Do not be that person. All right, so temperature has to be in Kelvin. Get used to the idea that as soon as you see a temperature, go ahead and add 273 to it. You might as well. And when you're looking for an answer, you will subtract 273 off of whatever you get because your answer will be in Kelvin as well. Okay, all right. All right, now on to the math. Love math. Math is what it's all about. And so if you look, there are all these guys called well, Kelvin to temperature, and you've got things like Boyle, and you've got Gay-Lussac, and you've got Henry, and you got all these guys who made all these gas laws. Okay, all these gas laws, but there is only one gas law that really matters, and it's called the combined gas law. And I'm going in a little bit different order than what the text does. I'm starting with the combined gas law, and we'll go on to the ideal gas law. And it goes like this. It's P1 V1 over T1 equals P2 V2 over T2. There you go. This is called the combined gas law. It combines all these troublesome people like Gay-Lussac and Charles and whatever. We don't care about those guys. All we care about is one equation to rule them all. Okay, we just need one equation. We don't need 3, we need 1. All right. And this is the one equation. This is P1 V1 over T1 equals P2 V2 over T2. Okay, so what you do is you plug in whatever it is that you have, and then you solve for whatever it is that you need. One equation. All right, now we should all be able to solve anything in this equation. Hopefully, if you made it through 171 and if you moved on to calculus and whatever, you can solve for whatever it is that you need. So if I was to solve for, say, P1, I would say, what is that? That's P2 over V1 times T1. And am I doing this right? Let's see, P2, let's see, I'm solving for P2, right? Okay, so that would be over, hold on. Let's solve for P, yeah, we're solving for P1. P1 equals P2 V2 over T2, and that would be over T, let's see, that would be T1 over V1. There we go. Okay. So we should be able to take, anything, and we should be able to just solve for whatever it is that we're looking for. All right. That was the whole point of that little exercise right there, is we should be able to solve for anything. All right. Now, fortunately for us, we usually don't have to do that. We usually don't have to take and rearrange, 5 things to get the 6th thing that we need. Usually what we do is we cover what we don't need. All right, usually that's what we do. We cover what we don't need. So what does that mean? What that means is usually we're working in pairs. Usually we're working in pairs, which means usually we're holding something constant, which means usually we're not only are we holding something constant, we don't even mention it in the problem because it doesn't change. Okay. And so we might say something like a gas at 25.0 degrees Celsius in, let's say, in a, let's say 4.00 liter container is heated to, oh, let's say, let's heat it up. Let's say 401 degrees Celsius. What is the new volume? What's the new volume? Okay. And you look at this problem, and this is our first problem out of this chapter. Okay. Now, and granted, we only have one equation so far, but we have to ask ourselves when we look at a problem, we have to ask ourselves, do I see pairs or do I not see pairs? You have to ask yourself that question every time. Remember when we did chapter 3, chapter 4? It was all about asking questions, wasn't it? Do I see grams? Do I see something going to something? Do I see these things, right? And it's the same sort of thing here. You look at it and you go, do I see pairs? And the answer is, why, yes, I do. I see a pair of temperatures and I see a pair of volumes. I do see pairs, don't I? I do see pairs. And so if you see pairs, this is what you need. Okay, you see pairs, this is what you need. This answers the question. What in the heck do I use, right? What do I use? Well, the answer is if you see pairs, you need to combine gas law. All right, you don't have to ask yourself questions like, oh my, do I need Charles' law? Do I need Gay-Lussac? Do I need Henry's? What do I need? No, you just need to combine gas law. All right, now I see a pair of temperatures and I see a pair of volumes. Do I see a pair of pressures up there? And the answer is, well, I don't see a pair of pressures. And so what I'm going to do is I'm going to go up here to my combined gas law, and I'm just going to mark off what I'm not using. I'm not using pressures, so I don't need them. So what's the equation that I need now? And this answers the question, well, what equation do I use? Well, here it is. You marked off the pressures. It's V1 over T1, V2 over T2. There it is. This is the equation that you need. Now, do we go ahead and just plug in our units? Just go ahead and plug and chug? No, because you are not going to be that person, right? Who plugs in degrees Celsius. You're not going to be that person. Please don't be that person. All right. Because if you plug in degrees Celsius for T1, T2, you will get an answer. Your calculator will give you an answer. And will it be choice C? It sure will be. It'll be choice C. And you will say to yourself, Mr. Pierce, give me my 100. I'm done. I'm ready to go to med school or whatever it is. And you'll get back your test and say, what the hell happened? And it will be because you chose poorly. Do not put in degrees Celsius. What do we need to do with this? We need to add 273.15. In this case, if we round that 273.15 rounds to 273.2. That's why I put in 273.2, because we're using rules for addition, right? And rules of addition, you go by the least number of decimal places. Sound familiar, right? We should know. My physics friends tell me, that when they get our chemistry students in physics, they say if they know anything, they know significant figures. They might not know anything from chemistry, but they can do significant figures. Now, I hear this literally from my physics friends. And so you're going to do significant figures. And so 273.15 rounds to 273.2, which is why we add that. And so this becomes 298.2 Kelvin. By the way, there is no degree in Kelvin. It's just Kelvin. All right, but you know what? If you put degrees Kelvin in there, I'm not going to say anything. All right, but just understand, if you put a degree in there, it's not technically, it's not right. It's just Kelvin. All right, and so we got 298.2, and if we do the same thing over here, we have, what is that? That's 674.2 Kelvin. Yeah, same deal. And of course, I'm assuming that that was a 0.0 there. All right. I was just assuming. We use the same thermometer. We should estimate out the same number of digits. All right. So I have in Kelvin. What did I say about Kelvin? Get used to the idea that everything's going to be in degrees Celsius. And the first thing you're going to have to do is convert it into Kelvin. Okay. That's what you have to do. All right, and so the volume, on the other hand, we don't have to do anything to that. It can be liters, it can be cubic feet, it can be milliliters, whatever you want it to be, just as long as you're consistent. All right, as long as you're consistent, it doesn't matter what the units are. So let's go ahead and plug them in. And so we say our first volume is what? It is 4.00 liters, and our first temperature is 298.2 Kelvin. I don't know what the new volume is, but I do know what the new temperature is, and that's 674.2 Kelvin. Now, we can solve for V2, and everybody in here should be able to solve for V2. Or we can use what most folks I have found over the years. I have no trouble with just going ahead and solving for it. I mean, that's what I do. I just say, I'm just going to solve for V2, and then I'll plug. But it seems like, at least in Eastern North Carolina, everybody likes to do what's something called cross multiplication. Y'all know what cross multiplication is, right? Okay, so we're going to do cross multiplication, which means we multiply these two, and then we divide by the other one, okay? And then we'll get a number. So I'm going to grab my calculator. And so I say, let's see, turn on my calculator. So I say 4 times 674.2 divided by 298.2. And I get 9. Let's not forget that there are units, okay? 9.04 liters. So there you go. We got 9.04 liters. How about that? Okay. Now, if you look at those numbers, 298 versus 674, do you notice something special about those numbers? And 298 is about 300. And 674 is about twice as much, isn't it? It's a little over twice as much, but did you notice what happened to the numbers here? You went from 4 liters to 9 liters. You went from 3 to a little over twice as far as the temperature goes. And so if we doubled and a little bit more the temperature, what happened to the volume? The volume doubled plus a little bit more, didn't it? Yeah. And so the volume and pressure, we'll do this in just a second. The volume and pressure is directly proportional to the Kelvin temperature. Notice I said Kelvin and not degrees Celsius, all right? Not degrees Celsius. It's proportional. So what does that mean to be directly proportional? It means that if you double the temperature, you double the pressure. If you double the temperature, you double the volume. If you half the temperature, well, you half the pressure and you half the volume, all right? They're directly proportional. They literally are. The Kelvin temperature. If you do this in degrees Celsius, you will get an answer. And it will be one of the choices, but it will be wrong. All right, don't be that person. All right, don't be that person. So we have the combined gas law here. So we can do just about anything with our combined gas law. And so we might do something like this. We might say, what is the pressure of a container? And let's write this out a little bit nicer. Let's see. That started at, let's say, 8.00 liters and 1.50 atmospheres if the container was changed to, let's see, what do we want to change it to? Change to, oh, let's say 4.00 liters. What's the new pressure? All right, so we're going from 8 liters and 1.50 atmospheres, and we're going to change the pressure to, some pressure, but we're going to change the volume to 4 liters is what we're going to do. All right, so we're taking the container at 8 liters, and we're going to squeeze it down to 4. And I want to know what's the new pressure. What's the new pressure? Okay. Now, as I have said before, you have to ask yourself, do I see pairs or do I not see pairs? And I know that we're doing now, we've only had one equation so far. And the only equation we've had so far is the combined gas law, and that's pairs everywhere, right? But you still have to ask yourself that question. And so I see up here, I see a pressure and a pressure, and I see a volume and I see a volume. I do see pairs, okay? So the equation that I need to use is going to be P1 V1 over T1 P2 V2 over T2. I know that's going to be the equation that I need. And so now, do I see anywhere in here, do I see temperature? And I don't see temperature, so what does that mean I need to do? I just ignore the temperature. Do you see how this works? You have one equation. Matter of fact, this is how I got through first semester chemical physics. Lots of equations, but really when you got down to it, there are only a couple of equations. And so you memorize one equation and then you use that, you derive whatever it is that you need. And it may sound hard to derive what you need from an equation, but actually it's pretty easy. Once you have the one equation, if you know the calculus or derivatives, as a matter of fact, that's what makes calculus-based physics is actually easier than non-calculus-based physics, because if you memorize one equation, you either take the integral of the equations or you take the derivative of the equations and you get what you need. This is why Newton, Isaac Newton, he developed calculus He was the guy who developed calculus like 400 years ago. Why did he develop calculus? Because you can take one equation and find everything you need if you know calculus. Okay, so it's the same thing here. I have one equation, I just cross off what I don't need. Voila. All right. All right, so we have that. And I don't see temperature up here, so there's nothing I need to do. And we have liters go into liters. And so we're at least consistent. We have to be consistent with our units. That much I know. All right. And so we'll just go ahead and plug and chug. Now, I don't think we can do cross multiplication here. So what I'm going to do is I'm going to solve for P2. And if I solve for P2, I say P2 is P1 V1 over V2. There it is. I'm looking for the new pressure, right? So I got P1 V1 over V2. And so now what do? All I got to do now is just plug and chug. Plug and chug. And so what do we have here? We got P1. Where's P1? P1 is 1.50 ATMs. What's V1? V1 is 8.00 liters. What's V2? Well, that would be 4.00 liters. That's V2. Okay. Now, I would expect that if we were looking for the new pressure and I took something and I squished it and made it a lot smaller and didn't do anything to the temperature, I would expect the pressure to go up. All right, as you squeeze something, the pressure should go up. As you expand something, the pressure should go down. And are we going to see that the pressure goes up? And the answer is, why, yes, we do. And I did the math in my head, and so this is 3.00 atmospheres. Don't even need a calculator for this. You go from 8 to 4, that's twice as much. It is, isn't it? And 8 over 4, 2, yeah. 8 over 4 is 2, 2 times 1.5. Yeah, sure enough, we get 3 atmospheres. And so sure enough, if you take an 8-liter container with like a piston, I guess, on a piston on it, and you just squeeze it, you're going to double the pressure. If you reduce the pressure by half, you're going to double the pressure. And that's what we did. We reduced the volume by half. And so we doubled the pressure. So this is the relationship between pressure and volume. They are inversely proportional, which means as one goes up, the other goes down. As one goes down, the other goes up. All right. So that is the relationship between pressure and volume, is they're inversely proportional. What's the relationship between volume and temperature? That they're directly proportional, right? As you double the Kelvin temperature, you double the pressure. As you double the Kelvin temperature, you double the volume. All right. So these things, they go proportionally. Okay. All right. So we should be able to use the combined gas law. Easy peasy, right? You just take it, you cross off whatever it is that you're not using, you plug and chug. You just go from there. You just plug and chug. Okay? Now, if you take these various laws, Charles' law, Gay-Lussac, whatever, if you take these various laws and you do a little bit of manipulation, you will end up with something that looks like this. Pressure times volume equals the amount in moles times something called R. PV equals nRT. Say it enough times and it will sound right to you. Just say it enough times. You go PV equals nRT. All right. This is called the ideal gas law. That's what this is called. It's called the ideal gas law. It has its own name. All right. And this is assuming, guess what? That gases behave ideally. This is why it's called the ideal gas law, because gases behave ideally, which means that as you increase the pressure, the volume decreases. Remember, we just did that a few minutes ago, right? And as you decrease the pressure, the volume increases. Okay, this is ideal behavior. And for ideal gases, this is pretty good description. For most of the time, it's one of these rare things that actually works in the real world. It's one of the rare things. Many things don't work in the real world. You can write down equations, they're supposed to work, but when you go do them, they don't work. All right, ideal gas law actually works pretty good. It's actually a pretty good equation. And so it's pressure times volume equals the amount times RT. Now, I'm going to give you a pro tip today. I'm going to give you a pro tip. I'm going to give you something that was never explained to me properly. I'm going to explain it to you. And that is, how do you pick the R? R is called the ideal gas law constant. All right. I'm going to reveal to you the secrets of the universe this morning. I'm going to tell you how to pick your R, because see, when I was in your position, it wasn't explained to me right, and so I would have about 50% of the time I would get it right, and 50% of the time I'd get it wrong. And what's a 50 on a test? 50 is not good. Okay, so I would never get this right. And so R, there are many R's. There are many, many R's. There are at least 14 that I know of. At least 14. There's probably more. But there's only a couple of them that we really care about. We'll go 3 sig figs. 0.0821 liters, atmospheres, moles Kelvin, and then you have 62.4 liters, millimeters mercury, moles Kelvin. All right, we have two out of many. All right, I want to make that clear. This is just 2 of many R's. There's actually another one, 8.314, and this is, what is that? Joules, moles, Kelvin. Okay, that'll come later. All right, there's actually a third one. This is kind of like an aside, just to show you that there are many, many R's. Many, many R's. All right, so how did we pick the R? How in the world did we pick the R? Well, look at those 2 R's that I just put down. And just look at them for a second. Just these 2. What do you see that's different? What do you see that's different? The pressure unit is what's different. Now, you may say to yourself, Mr. Pierce, how could you miss that? How could you miss that? Well, look, I was in your position at one point, right? I was there, and I saw this for the first time, and then it never dawned on me that the difference between the R's is literally the pressure units. Do you see that now? Of course, I've circled it. Of course you see it, right? But look, do you see what I'm saying? The difference is the pressure units. What do you see up here? You got a pressure, you have a volume, you have moles, you have some sort of R, and you have a temperature. What do we know about the temperature? The temperature must be in Kelvin. What do we know about the amount? It can't be grams. It has to be what? It has to be in moles. Now, I never said anything about the volume other than say that there were different kinds of volumes. But if you're going to do this calculation, guess what the volume has to be in? The volume has to be in liters. Do you see that? It has to be in liters. So we really have no choice in this equation. We either have to do our calculations in atmospheres or we have to do it in millimeters mercury, one or the other. So how do we pick our R? We look at the units. All right, that's how we pick our R. We look at the units, okay? So you don't want to just pick a random number. Don't be what I was. Okay, don't do what I did when I was in your position, which was I would just say, you know what, I don't know, but today it looks like 0.0821 might be the one I need to use. All right, don't do that. What do? You look at the units and you pick your R based on the units. Okay, that's another reason why I've said all along, I've said, whatever you do, always use units, right? Always use units. Why do we use units? Because we can cancel them, right? Well, here's another reason for you to always use units. Because if you don't use units, you don't know which R to use, right? If you don't use units, you don't know what R to use. All right, so let's take, it is almost 11 o'clock. Let's go ahead and take a break. And let's take a, let's see, you got 4. Let's take an 8-minute break. That'll put us to 11:04. Okay, 11:04. All right. Make sure you come back. I'll be back.